All right. All right. Think I should be connected. Just checking for voice. All right. Seems like my voice is working. Last time we used SDL to create a window and we had an instance open, which means a Vulkan instance, which means we have connected to the driver and we've asked for a Vulkan 1.3 version of the API because that has a lot of features and it's well adopted within GPUs. So from there, we're actually going to start moving to interfacing with the GPU itself, which means we'll actually, you know, uh, connect to the physical device I have. I have an integrated graphics card and a discrete graphics card, and we look through that. We'll actually iterate and we'll find that. But until then, so far we have an instance and a surface. We have destroyed both of it as one should, and finally destroying the SDL. That is left over place. I'm not removing that. So moving on from this point, we just have to get every single device that is available on my system, right? Uh, Vulkan has functions for this, which is we can enumerate physical devices, right? What this does is it asks the instance, i.e., the graphic card, for the devices that we have available to us. And it has a very unique sort of way of handling things. Normally, you might expect an array to be returned or some sort of a container to be returned, but that means it has to do allocation inside. And Vulkan instead wants you to do the allocation yourself. That way you can decide if you actually want to allocate something or not. And in order to do that, you need to know what the size is. So the enumerate device actually lets you call it with just the count. So you went 32T, the device count. So this is physical device count, which we haven't instantiated, which is completely normal. It takes physical device count as a pointer and we give it a null pointer. Okay. So unfortunately, because we're using Vulkan, one of the problems we get is we cannot see the definitions in the main window directly when I put things in there. But yeah, VK instance, physical device count as a pointer. So the physical device count, and finally the physical devices. We actually provide a null pointer there. All right. So it sees that it's a null pointer. It knows it doesn't have to write anything. Instead, it will just fetch the number of devices. Here, let's actually print how many devices we have. Do we actually keep format? I don't remember, but we can do it with SDL print. SDL has a log option. So yeah, inside log, I can say system found %UL devices, GPUs, right? And we give it the physical device count. So once that is done, let me just do something. Let that into it. I'm just trying to get the chat connected. Aha, done. So in case somebody actually texts, we have the message. All right, coming back. Found UI devices. This physical devices enumeration is taken from the instance. These are just, this will be just handles, but right now we are not allocating anything and there's nothing to destroy. So this is by itself. We can just run it once and in the terminal that it creates, we can see it found 2L GPUs. It's 2 GPUs, but I think I made a mistake somewhere. Yes, %U. I haven't used the C style formatting in a long time. 2 GPUs. We can close that. Now, to get all the physical devices, we need to create vector or an array of that particular size. So std vector, include vector, then we have to say it's vk physical device, because that's what we have, followed by the physical device count that we'll actually use for this. So physical devices with the physical device count, right? That creates an array with that many objects in it. We'll call the same thing over again, but this time we will actually pass physical devices dot data. Another thing we can actually do is in the first call itself, we can pass an array which is large enough that generally it will work, but a static size. So we can say an array of 8. This will actually lead to a non-success result, which might say something like incomplete. And then it will ask us, it effectively says that we have given you as many results as we could fit, but it requires more results. In this case, that wouldn't happen because we already asked it how many results it will give us, right? And we create a vector, which is a memory allocation. Not something we're going to optimize just yet, but it is something I will eventually optimize to use some allocators, because this creates, and then, we're going to destroy that memory soon. We don't need it all the way through the system. Anyway, moving on. Once we have all the physical devices, what we need to do is we need to figure out if this physical device is suitable for us or not. One of the things we need to check guaranteedly is whether it supports Vulkan 1.3, because we said we will be using Vulkan 1.3, right? That's what I actually mentioned at the start. So, physical devices, we can use a for loop for auto, and I don't have a problem with auto so long as it's used where you can actually see what it's trying to do. Physical device comes from physical devices. Then, right? So now for each physical device, I've added these braces because they're going to, as I said, they're going to not need this soon. So all of this is just local data. And all we need is that one physical device that we'll actually use. Anyway, so moving on. For each physical devices, you can see the physical device itself, even though, so we don't actually need to take it as a reference. Let's put the type in, right? The physical device itself is a pointer that doesn't have any functions on it. All Vulkan API has these pointers that are opaque. So you see, define handle. These are handles. You don't need to think of them as pointers. They could implement a Vulkan API where these are integers internally, right? We don't care. All we care is that we got a device handle there. So when we actually need to call functions on it, or like get attributes of it, we need to actually call functions on this, pass it in, and that will give us the results. Meanwhile, similar things in DirectX, for example, just gives you an object, like a C++ class-like object, and you can just access the properties in it. Anyway, so we can enumerate, I think it's get device features. I make some mistakes like this because it's physical device features. Okay. As for physical device, and it asks for the pointer to features. You don't have features yet, but we'll go through that. Physical device features, there we go. All of this gets initialized in here, so we don't care. And you can see, I mean, you can't see right now, but if I actually do something like auto x equals, you'll see that auto is void because this is guaranteed to never fail. If there is a physical device, it will give us a valid feature. If there is no physical device, it just doesn't give us anything and it doesn't care. So all in all, it can never really fail internally. Now, for these device features, we can check all of these are things that we will be using in our code. I actually got the wrong thing. I always make this kind of mistakes. Physical device properties. So features are the things your device can do. like ray tracing, not ray tracing, but like ray tracing related stuff, like checking if you can have bindless by using buffer device access and buffer device address, which allows you to just use pointers between your CPU and GPU. We'll get to that later. Point is, we need properties, not the other thing, not the feature right now. We will use the feature, so I'm leaving it there, but we don't use it right now. Anyway, once we get the properties, you can see the properties actually have API version. This we need. We need to check if the API version that it supports is similar to the API version we need. Note similar, not the same, because the API version can have differences in the minor. So in the patch, as you can see, make API version contains variant, major, minor, patch. Variant is 0. As far as we know, it will always be 0. Major, so here actually, major is the major number, so Vulkan 1, because we're just using Vulkan 1. Minor is Vulkan 0.3, so it's 1.3, and 0, because you have 1.3.202 and stuff like this. But all of Vulkan 3 will be cross-compatible, which is why we don't ask for the X, like the ending number, right? So API version, we want 1.3. Since we know that 1 is more or less going to be roughly the same, we will just say we can get, I think it's a macro on the C version, we can get API version major, So what we need to check is that the major equals 1, as we asked for Vulkan 1.3, API version, or better yet actually, VK API version patch, because the only thing we don't want is the patch, right? So we will actually take the patch out of it. Properties.api version, and this gives us the patch. So this is U32 patch equals to int32 that I can just. Okay. So patch, and all we need to do is remove patch from the API version. Start API version. XOR patch, or as you can see, it's 0 FFFF for getting the patch out. So we can instead simplify all of this. Yes, we're actually going to explore through these kind of things quite a lot. Log of 0x FFF, right? So it takes the last few bits, flips it, because it's it takes the higher bits and then does the AND with it, so it removes the patch. And what we need to check if this whole thing is equivalent to VK API version 1.3. Now what's this problem? Now it seems okay now. So all we're checking is removing the patch bits. So I'm actually going to create a const expression static patch bits equals, and we will put it there that way. UL32. So we'll actually put the patch bits, and then we'll say that not of patch bits and so on. Because it explains exactly what we're trying to do there, right? We're trying to remove the patch. Moving on. So if it's not equal to this version, then continue, because we don't care if it's not greater than equal to, then we don't care. All Vulkan API versions are backwards compatible. So we can use Vulkan 1.1 functions with 1.3, which means if the device supports Vulkan 1.5 or whatever in the future, we don't care, right? Like, so long as it's above 1.3. So continue means we just skip this one. We don't care about it. Second is for features. Again, I will check if the features dot we found the features later. I think there are more left in the properties. Properties dot device type, which is device type, physical device type, CPU. We don't want CPU, right? We want to choose something that is not CPU, because otherwise you have things like LLVM pipe, I think it's Lava pipe, which is an implementation of the Vulkan API on the CPU. It's relatively very slow, but for testing it can be quite nice. We can actually choose to use it sometimes, but for now, I will just say that if it's equal to the CPU, we say continue. All right. Next, again, if properties dot driver version, driver device name, I don't care about those things. Device type, we do prefer discrete over anything else. And so we might actually sort it that way. So device type, and we can switch instead of doing if. So switch, we can use the other complete because no point writing everything manually, right? So if it's CPU, we continue. Okay. I'm not sure if continue. Yes, I think continue works properly. I don't use continue and stuff often. So let's actually verify this. And closing the loop. So looks satisfying. Device type, virtual GPU, discrete GPU, other, again, let's skip other, we don't know what it is, right? Maximum is not a real value anyway. And no physical device type will actually be maximum. Oh yes, let's see that plus 23. We don't care about this. Again, we continue. Cluster disclose ends here. Integrated GPU, discrete GPU versus GPU. We can actually support all of these. And in such case, we sort it because integrated GPU is not as preferable as discrete GPU, for example. A virtual GPU will be even less preferable. So in order to sort, we would like to keep a bit of state outside here. So UN32T points, max points, 0, or -1, UA32T, replicate device, physical device, chosen device. We leave it to take null. So that's weekend null handle. It's just null pointer, right? This, as you can see, is a macro for null pointer, but it explains things better, let's say. All right. So integrated GPU, if points, which is max points greater than 1, less than 1, then max points equal to 1, and so on, right? We will do it like this for now. Generally, you will sort it quite well. You'll try to figure out the best thing possible. you will filter these properly. In my case, I'm going to take a quick shortcut, which is I will just choose my discrete GPU every single time. But at some point off screen, I will actually write the device selection. So anyway, we just move to physical device. User device. Just leave it to null pointer, right? And when you find discrete GPU, chosen device equals the given device physical. And that's all we really care about. So we don't need the switch case. We just need an if device type equals pk physical device type discrete GPU. Do all of that. Okay. This is a shortcut. Definitely complete your shortcut. And this is something I will eventually come and fix. But right now, not really important for me to get the device working. Now, the next is physical device, which is a logical device. What does a logical device mean? It means it is the interface that we have to talk to the GPU. So while instance is the interface to the driver, the device, not the driver really, it's more of the thing, it's called ICD, installable client driver. Basically, it's the thing that sits on top of the driver and it interfaces with each of the drivers. That's what instances are. While device talks to the actual driver to talk to the GPU itself, right? There's a logical GPU. While physical device is the actual physical GPU machine device, PCI connection, and all of that. We can actually print the devices that we have. So might as well do that here. So STL log device GPU %s. So let's just leave it to %s. Physical device properties, which is actually in the next line. Dot device name, right? It's 56 characters, but should be enough to see what the devices are that we have available. See, I have a RTX 4070, that's my discrete GPU, and Radeon graphics, which is my integrated GPU, because I'm running on a Ryzen machine. But I can also print more things out of this. But anyway, I have to check for presentation support. I should do that. I should probably do this. So it has to be a discrete GPU. Otherwise, we continue. So then if properties dot how do we check surface support? Surface VK get surface present physical device surface present load KHR. Okay. Yeah, I should be checking the spec for this, but things I've been doing very often that I remember how to do. Physical device surface. So we created the surface. What this does is it actually goes and checks with the system, like the window itself and the GPU, and tries to see if the GPU can actually connect to the window or not. Which means depending on the GPU that's connected, that can actually show things on the screen, you might actually get different devices that may or may not support this, right? Certain devices are made to run without GPU, as in like without actually displaying anything. For example, the Grace Hopper cards that NVIDIA has for ML workloads and all of that, they're not built for graphics and rendering. They're built for ML, but Vulkan's supposed to work on it as well. Anyway, so we move on. We check present mode count and we check how many present modes, like what present modes it has. Hold on. I think this is the wrong one. This one checks all the present modes we have. That includes like vsync and all of that. Surface support there. But what was the weird thing? Queue family index and whether it supported or not. And that actually requires us to go through each queue. So what is a queue? Each queue is a separate way to talk to, not talk, but like to provide commands to the GPU, right? So each CPU command, each command that is generated on the CPU will be written to a list that will be forwarded to the GPU through a queue. And you can have multiple queues. Each queue will be executing things roughly independent of each other. I say roughly because not all of these queues are physically available. Some of them are logical, so they exist in theory, but in practice, they just are one after the other or one at the same time, concurrently as the other. But anyway, so for queues, we have to do VK physical device queue. Look, VK. Okay. All right. One of those things where you actually have to check the specification again. Device and queues, queue creation. Nope, that is not the physical devices. Physical devices. So physical device properties. Then you have physical device properties. The few things in there. These that are specific to each Vulkan version. So you can see they have Vulkan 1.4 properties, device ID properties, KHR, driver properties. We're not actually checking any of these. PCI bus. Again, Vulkan's very in-depth. We don't need most of this. Yeah, we're going also matches indeed. It's execution model queue. Here, that. Right here. Physical device. Queue family properties. Get physical device queue family properties. There it is, right? So physical device takes the count of queue families, which since we don't have, we will actually take UN32 count. Oops. UN32T queue family count was 0. I mean, we can actually do that. Queue family count and properties as well. So here, one of the things that is, let's say, something that we'll end up doing if we actually create a vector is we'll keep reinitializing and reallocating the whole thing every time we iterate through this whole loop. So allocate, deallocate, allocate, deallocate. So instead, I will actually create the vector up here. It's a cheap, very cheap, and maybe properties. It's, it's a very cheap optimization, so not really very premature. The teasers. Look. So we take the number, then we take Q family properties dot resize, and we resize it to the given size, Q family count. Then we can actually do the iteration again. And we provide the Q family properties dot data. And it will write in there and overwrite whatever we don't care about. And so on, right? Another thing that you can quite easily do is, since Q family properties is per Q family, each Q family tells you different types of features that are available in a queue and how many queues you can create of that type, right? And when you iterate through it, I'll actually print the properties so we can see and we can go through it. But at the end of the day, most devices do not have more than 32 queues, current day and age. And that means the number of queue families is going to be even less than that, right? However, if we just create 32 of these all at once, at the end of this particular block, we don't need it anymore. And we can just use an array instead of a vector, for example. We're not doing that, but I'm just saying that's a very easy optimization to do based on knowledge you have of existing devices. Problem with this is, in the future, long time later, when there's more queues, let's say, this might become brittle, right? But I mean, you can always come back and correct it if it's that many years in the future that you're still using the code. Anyway, so surface, now we will provide a queue family. So again, here it's a for loop for queue family properties, QFP in the queue family properties. Use the if and not. So we actually give the QFP dot, it's here, QFP dot index. Index is an integer that comes from the outside. So when you hear Vulkan getting a bad rap because it's difficult to use or complicated, it's because of this, right? You have to go through a lot to really set up the thing before you can actually use anything out of it. It's not necessarily a bad thing, right? Is Surface supported? Because you can only write this once. Once you have written this layer, you don't really need to write it again and again. It's just a thing you have available to you. So we can boot actually. It's a 32-bit boot. The main reason that this is used instead of normal Boolean is because GPUs don't often support uh, anything other than 32-bit stuff. So in fact, it's a Vulkan feature that you need to enable to have 16-bit and 64-bit in the device. So again, this I've done if, but it's actually check. It shouldn't fail generally, but we can check what the criteria for this is. So valid usage, count as return must be there. Index must be less than the count. The get first to the SQL file packages. Yeah. The result it gives you is these three, right? Out of host memory, if we run out of memory on the CPU, not happening on most PCs because we have virtual memory. It's 2 to the power 64, right? It's not happening. I mean, we can run out of actual RAM, but the allocation will not fail. It will just throw the some of the memory into swapped and allow us to have the actual RAM for use. Device memory, this can happen. Even though GPUs do have some amount of virtual mapping and stuff, they can't, you know, uh, do it as versatilely as CPUs normally do. Not can't, it's more like they don't because it's not required. Surface loss is if your window closes or something like that happens. So if you provide the surface and the surface is just not responding, all of these are to us fatal errors, right? If memory is out, we can't do anything. And if surface is out, I don't think there's a point in actually looking at creating our window at all. Just quit and we get done with, right? So if it's supported, now we know. Since we already have the Q family properties, we should also check the Q family properties. We also increase the Q family index. Q family index. There. Properties dot. So you can see Q flags, Q count, all of that. Q flags is the important one. So Q flags and we take Q E flag and Q compute bits. So Q flags, and if it has compute bit, it means this particular queue supports compute operations. So if I want to do anything with compute shaders, do GPU programming, this is what I need, right? So if it has compute bit, I don't even need to check anything because if it's 0, it's gonna be considered false. So if it has compute bit, then we can print out SDL no device as compute. I'm just gonna put it like that, compute, right? And I will print the index first. So Q SND, the Q is Q family index, so you got compute, and we need to copy paste it for each of these. So compute, graphics, and transfer. These are the important ones. Graphics, compute, and transfer. This is easier in DirectX 12 because they have three types. There is direct, which says it is graphics, compute, and transfer. There is compute, which has compute and transfer, and then there is transfer, which only has transfer. Generally, each of these is used for a different type of task. So the graphics queue normally will have compute and transfer supported on it because this kind of, and present as well, because this kind of queue can do all of it, right? It can do graphics, it can put compute shaders in the middle, it can do transfers, copy between different memory locations, CPU to GPU or GPU to GPU and stuff like this. And present, which is to show things on the screen. It is mandatory for at least one graphic device to have present support on it. Graphics queue. Or is it all of them? But at least one anyway. So the other type of queues, as we'll actually see once we run this, surface supported, and if it is supported, we can print surface supported. We can print present, and let's run it. Let's see what happens. Actually, we never did it. Why did it now? So, device family properties. Return the void. So this is fine. These both, if it's not discrete, then continue. Remove that. If their version is not citizens, that is a bit weird. So I'm actually going to do the also loud here. We stopped doing the continue formatting thing. Right. But we get back to it in a sec. So personally, API major for the API version. Major, minor, and patch. I've taken dots by mistake. I'll format it so that it's easy for everyone to read on the screen. Major, minor, patch. That should be fine. Let's check what's happening. 1.4.303. Radian has 1.3.292. And we can see the queues. So the Q0 on the NVIDIA device has a graphics, has a compute, transfer, and present. Yes, I wrote this set by mistake, but yeah. The second, like the queue number 1, has just the transfer. So this is an asynchronous transfer queue, right? Normally, this allows you to copy things from your CPU RAM to your GPU without having to deal with anything in the middle. So it just, allows you to copy things outside of when your GPU is rendering something. When you use the same queue, it does tasks one at a time, right? While if you use this queue, it will do a faster transfer, a TMA transfer as it is known as. And, it's more optimal for that. This one has compute, transfer, and present. I don't know why it has present, but compute and transfer are normally together because you need transfer if you're doing anything else, right? So this is a compute queue. This is an asynchronous compute queue. The integrated AMD Radeon graphics has graphic, compute, transfer, and present. Then a compute, transfer, and present, similar here to this. And finally, a DMA transfer queue. This one not very useful as far as I know, because we are sharing RAM with the main device, but you can still do other transfer operations on this queue, which can be good depending on your use case. Like for specific use cases, it can be useful, I suppose. So yeah, the API version has been printed. We know that we had a problem with checking the API version because it's a bug, right? This is fine because we need this. We want that API version. If this is less than 1.3, we'll skip. This is why it wasn't what. This is why it was going through the whole other thing, right? Now, what else do we need to look at? So the tune, there's dashes here. This is just pure raw info. Not sure if we need it, but nice to have also. I will change the SDL log to SDL info. That is the SDL info. I think it's a log info. Yeah. I'll just manually do that. Log info, let's check it again. We will go back to this logging like that. For now, at least. Anyway, so now we know that present is supported. We have a queue that supports everything. And we will use that particular queue. We need to know that particular queue when we create the device and, get ready with that. So what we will do is we will actually take the queue family. Primary, let's call it direct queue family. This is DirectX terminology, which is a bit weird. to use when you're looking at Vulkan, but consistency is nice sometimes. So yeah, we will put two games here. It works as graphics support. It's alls copy paste support as compute transfer design. Now some of these are obviously easier to do by just merging all of these together. But it's fun to have, let's say, less than nice looking code that is easy to understand, right? So all we have said is that for these flags, we check if each of those flags exist, and if as graphics and as compute and as transfer and as present, then we Q family index equals Q family index. Direct Q family index equals Q family index, right? So you just assign that. Q families keep rotating further. However, every time we actually assign a new chosen device, we need to reset that, right? So direct Q family has been done here. Of course, once direct Q family has been done, we can break the whole thing. We don't need to be rotating through. We found the Q we want. Yes, we can limit const, so we make it const. This continues. Yeah. So if at least one queue has everything supported on it, we can use the device. We don't have any other real requirements on this, except being discrete. So we will add that. If actually not even discrete, dot device type not equals properties dot we create device physical device type CPU. And then we continue as well. And finally, once these two are done, the device that is left here is our physical device. So chosen device equals physical device. And that will assign it and keep moving on, right? Now, at the end of this entire thing, right, what we have is we have a physical device and the index that we will be using. What we now need is to create the actual device, which we do by doing vk create device. Okay. Physical device, create info, and stuff like this. So first things first, hold on. Device, take the physical device first. So that's chosen device, create info. So it will take a create info. And finally it takes allocation callbacks, which is null pointer. This is fallable. It can fail, and it can fail pretty miserably. But if it fails, there's nothing we can do because we cannot use Vulkan anyway. What are we missing? Ah, yes, of course, the device itself. Create info is also a pointer, so we give it that. And we need to create the create info. So vk device create info constant create info equals. We open that. Create info dot reserved initialization as type is vk structure type device create info. Should type device there. Should have, at that point, I could have just written the whole thing myself. It would have been fine. But anyway, queue create info count. So how many queues do we want, right? In this case, we will just use one queue to create info. Create device queue create info. But later on, we can come and add more queues if we decide we want to do the asynchronous stuff. Structure type device queue create info. Index is null pointer. Flags is 0. Queue family index is the direct queue family index. Queue count is 1. We just need one count. One count. And the queue properties would be an array where each queue gets a priority, and each priority will be the same in this particular case. So float priority equals 1.0, and we'll just pass 1.0 for everything. Since there is only one queue family index, it's fine, right? Direct queue family index may not be initialized. True that. What we need to do here is assert that the chosen device exists, right? Because if chosen device doesn't exist, then the queue family is invalid, first of all. And secondly, we don't have a chosen device. So we don't have a physical device to work with. So we cannot create a device anyway. Create info, this must kill something, device create info. Even though this would be fine normally, we'll avoid it. You create info, you just have one, and we have the queue create info from up there. Enable layer count, 0, null pointer, enabled extension counts. It says device extensions. We will not be using any at the moment. Enabled features. This we do need to provide, so features. But so which features are we enabling? So we get features. So it also is actually the same features, but features equals big thing dot consider initializations. We can see there's a whole bunch of features that are available that we can turn on. Out of all of these, the only one I will turn on at this moment is sampler and Azure properties. Right? Hold up. There's one more. Depth. Right? Everything else we can leave to defaults. Since the structure will be initialized to 0, the defaults are all false. Got it? So yeah, the features have been provided. We can create device. This may succeed or may fail, but in any case, we will have our device at the end, right? So we'll place the device up here because otherwise the scope finishes there and the device is no longer there and will also no longer valid. Similarly, once we have the device, what we need to do is we need to quickly get device there. So we take the device, we take the queue family index, which we got from there. We take the queue index, which is 0 because we only have one queue that we take, and the queue itself. So that's it. That's a direct queue, right? Again, we can check. And we need to create this direct queue up here. Direct queue. Are you Indian? Perhaps. Does that matter? Anyway, which result doesn't match a device queues, and there always is a device queue, more or less. I mean, it can fail if you have an incorrect value, but that's a logical error. Yeah, it's void because, must be less because it's invalid usage. But yeah, nothing you can really do if you make a mistake with it. No. Once you have the queue and the device, we need to make a mirror of it after the while loop, which is to destroy the device. So that's vk destroy device, and go at the device and deallocate this null pointer. Okay. This, when we turn it on, we will have created a device. So I know it doesn't do anything, but yeah, the device has been created. So once we reach this point, 1 second, hold on. So once we reach this point, the next step is to actually be able to present to the screen, right? To be able to present, not to actually present. So in order to show this on the screen, to show anything on the screen, we need something known as a swap chain. A swap chain allows you to create images that you will present to the screen, but they can't be immediately presented. They have to go through the process that the system has. And in this case, it's known as a swap chain. It's abstracted using the swap chain. Different devices will have a different kind of swap chain implementation, right? So, swap chain. But since you can use Vulkan on a headless device, something without graphics, as we talked about, present, as you can see, is not a part of it. Surface and swap chain are extensions. Now, once we have swap chain, again, we come to creation. So we create swap chain KHR, takes a device, takes swap chain create info. So we can call it swap chain create info. And it asks for callbacks, which will be null pointers on this swap chain. PK check. So we just ensure that we are handling if there's an error. So let the VK swap chain create because we'll create info KHR constant info designate initialization. So this was a big one. VK structure type swap swap chain create info. There's plenty of those. KHR response. The next, we don't have a next. Flags is 0. Surface is surface. Min image count. Okay, min image count can be a little annoying. So we actually need to get certain properties to check what is the actual min image count that we can have, right? So that comes from we take chain. Not that one. We click create swap chain KHR. Swap chain create info KHR. And then image count. We're going to start with the minimum number of images. The implementation will either be a swap chain with at least as many images or will fail to create the swap chain. So physical device surface capabilities. So we need to get this, right? physical device surface capabilities. Physical device. So we did not take the physical device out. We only left the queue and the device, but instead we will bring out these parameters. Chosen device, and we'll rename this to physical device. That clashes there, right? Undo it, change chosen device to device in use. And we move to the inner scope, it says, but we will not. We need it here. Surface, and capabilities are here. Capabilities. It does result a result, so check. Check. Capability to give. Okay. Surface capabilities. Yeah, sure. Capabilities. We get it filled up, and then capabilities dot minimum image count. There's also max image count. Sorry, that was max. This is min. The min image count is a max image count. I would like to have 3, so we went the Swapchain image count was 3. So assuming, let's say, I would like to have 3 count. Max image count is either a maximum or it is 0. So the behavior should change accordingly. First of all, if max image count is greater than 0, then swapchain image count equals swapchain image count. A steady min between image count and max, right? So at the end of this, we have upper bounded if required. And lower bound is compulsory. So we will not even look at it. Swapchain image count equals STD max of capabilities with swapchain image count. Now I am building a rendering engine. You can see an older one on my channel that I have a demo, like a little bit of a demo for. I left this for a while. Now that I'm back and doing this as a hobby, I thought I might as well stream, right? So once this is done, this will be the correct image count. And we've asked for it. If there is 3, then we'll exactly have 3. Otherwise, whatever is the closest valid value, right? Image format. Again, we need to figure out what format is feasible for this. So capabilities dot, it's not capabilities. VK surface formats. We'll just get physical device surface formats KHR. Again, we need the physical device in use. We need the surface. We need surface format count. Surface format count. And surface formats, which should be null pointer. So again, just like previously, we do this enumeration using the step-by-step process, which is fairly normal. No, computer graphics, similar to video game rendering, for example, not video game, 3D graphics. Vector surface device format. So that's VK surface device surface formats. Actually, it's VK format itself. So surface format. Noodle is my left out. Surface format dot data. And Once we have this, we can go through them. My preferred format will be VJ format. Equals actually undefined. We'll start with undefined, right? And for each of these, we clear surface form. Wait, each of these surface formats that we get, we will check if the surface format color space is okay, surface format color space. sRGB nonlinear KHR. So this is SR, or it's deprecated. Yeah, it was the new one. Yes. Is there a video that I can start it from? From my channel, the live streams are available on video on demand, but this is not me doing tutorials. This is me just programming and explaining what I'm doing. So if you really want to learn, you're better off following tutorials. There are some like Brendan Galea, who does Vulkan tutorials. There is Ludovic Fossel, who does DirectX tutorials. They are very nice. There's also written ones like vulcantutorial.com or learnopengl.com. For books, there is Frank Luna, who makes DirectX books, which are quite nice. So yeah, plenty of documentation if you want to start on. I really recommend learnopengl.com. I think everyone should start there. It's the most well-made website I've seen on this topic. Yeah, so if the color space is nonlinear KHR, so this is sRGB color space. This is what most systems will normally, support on a screen. There is linear. They might have linear too, but sRGB is very common these days. So we will look for sRGB. So if we have sRGB, then the format associated with it can be put into the format. So format surface format dot format, right? And another thing that I do, which is like a hack, is if surface format equals VK surface format. Again, there's a generally there is the VK format R8, G8, B8 as well. Sorry. Normally there's like a proper selection for this. You can do it based on what you need. There's a lot of formats available, but I don't particularly care. So this would just be great. So if we have this format available, great. If we don't, then we'll deal with it. Actually, this will give us an error. I want it to give us an error. It needs to be VK surface format. Surface format KHR, right? For each of these, there's format equals surface format. Surface format dot format is sRGB, then we rate here. You can do it this way too. So we basically say we need RGB8, or if we find VK format B8, G8, 8 sRGB. So BGR is also a pretty common format, right? So whichever of these is the first, we just use it and we break, right? We don't particularly care. Otherwise, we just pick the one that does support sRGB. So if surface format dot color space equals VK color space linear. So you can see there's no linear here anymore. It's just a search you do, where we don't want to look for the other ones, right? So if this is undefined at the end of all of this, was format equals UJ format undefined. So if we do end up with an undefined format at the end of this, we just assert false, right? Assert format is not equal to UJ format undefined. Let's say color space format and format dot color space image extent. Again, this is the size of the image. The size of the image. So this is image count calculation. Image size calculation. Image size right now will be the same size as the screen that we create. So we create a window of size 1280720. We'll try to create a swap chain of the same size. So we can extend 2D swap chain extend equals the width as an initialization. Width is I think we have the width and the constants of width and height caps. So width equals width, height equals height. These are limited. So these two are limited. I cannot just arbitrarily add whatever width and height I want. I need to restrict them as well, just like we did for the image count with the min and stuff. We will do it here. So again, swap chain extend, swap chain capabilities dot min extend, right? Min extend, we are going to have, so what the line really equals this, because I don't want to keep writing that again and again. Or maybe I can. When we recommend height, we're just going to break it into pieces using the destructuring, max width, max height, max image extend. Then we can do the swap chain extend. Right? So swap chain extend, std clamp. Do we have clamp? We do not have clamp. So I'm just going to create my first utility function, which is auto clamp std let it tag control auto stage. I'm not gonna do that. So template three three and yes, this all of that. We'll do that later. You know that utility why so this is val, this is main val, this is UL 32 key max val, return std min between the max val and std max between the val and the min val, right? So min val tells us, that will clamp it. So it will be between two values. So the template is class and error, so we will just that. And these are constraints. So if you're doing it with doing properly, we decorate the constants. Extend over here. Swap chain extend. width equals plan main width. Nope, it's Swapchain extent width main width max width height 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 height, and that should be fine, right? The reason we cannot clamp this is because the max image count can be 0. Option extend can be moved to inner scope. Yes, because we're not using it ahead yet. Option extend can be used here. Image array layers. 1. We don't want an array of images. We are not using VR, for example, where you will have more than one windows to show and stuff like this. This is just a single normal computer screen. We only have one layer required. Image usage, okay, image usage, color attachment width. I think that's all we need here. Swapchain creating for image sharing mode, we care image pairing exclusive. Sharing mode exclusive. Q family index count, so that is direct Q family, because that's the one we're going to use to present. Right. Actually, this we don't care about. So 0 and null pointer. Those are required only if you're using sharing mode concurrent, because concurrent means the same image can be used by 2 different queues at the same time, but we will only use one queue in this particular thing, so we don't particularly care. Surface transform, flatbeds. Flatbeds identity bit feature. All this does is it says no transformation. Composite alpha. Again, we'll take composite alpha. Opaque bit KHR. I believe it should be opaque bit KHR, but we can check the spec as well. Should composite alpha. Indicating authorities when this surface is composited with other surfaces in certain Windows systems. So when you have, let's say, some fancy things like Hyperland on Linux, where you have transparent windows as an available thing, you even have it on Windows, I think. You can compose it with an alpha so that you can make it translucent. Let's check. I think the acrylic theme, okay, I don't have acrylic theme anymore, but the acrylic themes on Windows can actually do a little bit of a see-through. Okay, present mode, mailbox. This should be looked for, so result. So we will actually look into the present modes, just like surface format. BK present mode. PHR, remote mode, or auto present. These are all Uing32 emails, so we can copy them by value and it's not a big deal. But we need to get the present modes. I think those are in the enumeration as well. So we're just going to copy that and edit it. Rules. So we realize the rule surface when out. This one, the change. Present mode. Right there. Present node tag, present node code, present nodes.data, present nodes.chr. So this is done. We get the present nodes here, and each present node. Yeah, an intentional copy. We don't particularly declare. So that's the iteration present mode. Okay, nice. So present mode editor, and now we just need to check if we have the present mode we want. So if present mode is equal to UK present mode KHR, let we get present mode FIFO relax KHR, then present mode. Oh, that's a bug. What's your problem? Oh. So if present mode editor happens, if it's FIFO KHR, then present mode equals present mode editor. And we break here because FIFO relaxed is fast, but it's also, kind of just works. So we can actually just look at FIFO relaxed, but basically immediate is immediately show the thing. It results in tearing. It's no VSync at all. Mailbox does VSync, so it cannot tear, but it can have not incorrect, but sort of non-consistent frame timing, because if you do not exactly reach the VSync times, you will end up skipping frames until you get there, right? So if you're rendering, let's say 5 times the VSync speed, so you're doing 300 FPS on a 60 FPS screen, you will get every fifth frame rendered to your screen during the VBlack. All right. FIFO will keep putting the FIFO will keep putting each image one after the other. And because of this, FIFO will render the screen at 300. The 300 will come down to 60. FIFO will guarantee that you will stop and you'll wait until the next image comes in. And so you will run at 60 FPS. It's VSync that will limit your speed, while Mailbox will let you render much faster. FIFO relaxed generally waits, but if it has already passed, it just goes ahead, right? So it can tear, but when it's not tearing, it's much faster than what is possible, and it still waits, just like Mailbox. Also, just like FIFO, unlike Mailbox. So yeah, relax is generally preferred to be used. Otherwise, we know FIFO exists definitely, because that is required. This is forced to be supported. And lastly, we can check if VK present mode mailbox to HR is available. So what we'll do is, if mailbox exists, we will use mailbox instead of FIFO. But if FIFO relaxed exists, then we will use FIFO relaxed, right? And that is guaranteed. That's the highest priority. So present mode has been done, create false, and old Swapchain is a null pointer. What is old Swapchain, you ask? So every time we create a Swapchain, it is of a particular size that is written here in Swapchain extent. Now, if you change the size of your window, you want your rendering surface to change size. When the rendering surface changes size, your Swapchain is no longer correct, right? So if in a game, you change the size of your window, the Swapchain will 100% change alongside this particular process. And that sounds a bit weird, considering these days we set our own resolutions for rendering, and you also have DRS, dynamic resolution scaling, which automatically reduces the resolution if your computer cannot match up to, let's say, 60 FPS or some other limit. But what happens is they don't actually render on the surface of the Swapchain. They render on a different image, and then they copy this to the Swapchain. And the Swapchain is still at the same size of your screen. So even if you use 720p on a 1080p screen, right, or 1440p on a 4K screen, the Swapchain is still going to be 4K because your screen is 4K. If you're using full screen, of course. Now, once this is complete, we try to create the Swapchain, and if we succeed Swapchain creation, we need to destroy it. So chain, this is destroy, Swapchain creator, device, swapchain, allocator is null pointer anyway. Yeah, and you can run it. There is an error. Format is not equal to null. I think that's a problem because it shouldn't be undefined. So, oh no. That is incorrect. That is entirely incorrect. The logic was correct in the first place. So, assert that the format is not undefined, but it does say that the format is undefined. So, this means that we did not find the correct surface format, right? Uh, So we can look at the documentation. Things might have changed since the last time I did Vulkan stuff. Surface formats. This is a long one. This one. Surface formats. With the ability to extend. Yeah, we don't care about that. So surface formats, we just get the surface formats. If we can Google surface list query. Yeah, we're not using that. So let's just look at surface formats. We get all of them. Material null pointer of the value. These are just explanations, but not the details about the formats and the color spaces. So color space. This is the non-linear KHR. G surface. So we should have definitely the non-linear KHR surface, right? So we can actually print here STL logged space SRGB found, and then we can also check DH8R8 SRGB. Yeah, there's always that option of doing this irrespective of which format it is. I don't think there's a ULOR version that is compatible. So you can see there's a lot of these. Mostly we care about the sRGB versions since we are at sRGB. Is there any other ones that are sRGB on this? So we don't care about those. BH8R88, BH8R8A8. What's the difference? RGB8, DGR8. ARGB, we don't care about those. These ones are all very, very unique ones. Most the sRGB won't support it. The basic non-linear sRGB that we're looking at won't support it. Those RGB8 versions is right. What I can do is I can just print color space found, and I can just print the format, right? So surface dot surface format. Surface format dot format actually. We end this. Yeah, okay. But okay, hold on. It went to format dot format. It reached this place without going through these. Why might that be? Can put a debugger on that. What is the surface format? So size is 0. Surface format count is 5. Oh, no. I don't, I forgot to resize the array there. And if I made this mistake here, I made this mistake here as well. Percent won't count. We can check. Swapchain KHR has failed. I don't care right now, but it found 37, 44, 64, and 43. Right? So 37, 37, it found this. 44, it found this. 37, 44, 64, and 43. So 64 is here, and 43 is here. RGB A8 sRGB. So it found the correct one. Driver's function pointer was null, returning the success was Swapchain extension enabled. No, it was not enabled. And this is another one of those things, right? So we need to actually enable Swapchain as an extension because it is an extension. All extensions in Vulkan need to be manually uh, declared. So device create info right there. We see you have extension count is 0. Well, it should be not 0. So we're actually going to create a little std array of enabled device extensions. Okay, device extension. Retail swap chain extension name. So this is a macro. It literally just tells you that extension name so that you don't have to manually write the string. It count template reduction. Really. Those count bolts small. And all sizes one. It type is incomplete. Oh my god. It's weird. We hit a normal array. So extension count is count of the result process for this that I recently found. It was quite interesting. But anyway, let's not use those funky entrances and all of that. Who knows which compiler supports it and which does not. It's an incomplete type, it says. It has an included array as well. No, it doesn't need to be. Now it can do the type reduction. Enable device dot data, extension count, so it's dot size, and extension names would be dot data. So yeah, this here will give us IST, while this wants a urent illegal. That is a conversion warning, but okay. That's the old one there. We should close that. No. That's the new one. No errors, right? Everything works, opens and closes fine. Working configurator. You can check this. So once it's on, it will give us more details on the mistakes we make. So far, so good. We will just have info, we don't have any errors. So we're fine. That's the surface, right? We've created most of the things that we had to so far. Ideally, now one of the things, well, the next thing that should be done is to take the device and then create a command pool and then command buffer. These allow us to actually send commands to the GPU. And the only command we really need to send is clear. And then we can clear the screen and we can move on, right? So, yeah, normally I would like to stop here because it's been a relatively long session, but I might extend it just to do the command pools and all. Think I should. So let's do that. Command pools. Okay. So a VJ command pool is nothing but a memory allocator, right? That allows us to allocate command buffers because command buffers are hot paths, right? You allocate a lot of commands every single frame. You keep doing it over and over again. And you don't want to allocate new memory every single time because that is costly. So what command pool lets you do is it just creates a lot of memory, but actually it doesn't create a lot of memory all at once. It creates some memory. It starts allocating command buffers. Each command buffer then allocates some of the pool's memory for itself. And command pool keeps growing like a vector. But at the end, it empties itself. That's called reset. And then you can start making new command buffers, like allocating the command buffers from it again. This one, again, is a bit different between DirectX and Vulkan in quite interesting ways, but we're not going to get into that. So we can command pool and we're going to create command pool. So that is we can create command pool. Takes a device, we already have that. We create info, so that's command pool create info, allocation callback, which is a null pointer, and command pool as the thing at the end, right? This can fail, so we can check at the start and at the end. Either this, and what we can do is we can also just swap these with. Sorry. Yeah. So we can do is we can copy that. We take command to create info. Again, this is constant. Start takes designated initialization. S type is VK structure type command pool create info. The next is right now in this particular case create flags. So we can command pool. We can look at it. We don't actually need command pool flags right now. So there's a reset command buffer bit. No, wait, hold on. We will use transient. So transient bit says that this command pool will not be used, not have memory that is allocated for a long time. So when you allocate command buffers, what you're telling here is I will keep allocating, deallocating, allocating, deallocating, and this will keep happening. And that is transient. That allows the driver to optimize to use the command pool that will be more performant for this task. Alternatively, you can leave it and then it will be a command pool that assumes that is more general purpose. It can make assumptions like there might be data that doesn't get deallocated that fast, right? Anyway, queue family index, direct queue family, because this command pool will create command buffers for the direct queue. It's the only one we're using right now. Now that we've created command pools, we need to create command buffers. Now, most of Vulkan's handles that we've created so far are what are known as internally synchronized. Or actually, they're not called anything, but basically they can be used across multiple threads without any problem. Command pools, on the other hand, are externally synchronized, which means they do not do any synchronization. If I want to use the same command pool on multiple threads, I am the one responsible for making sure that each command pool and the command buffers have mutexes applied on them so that they don't, do memory access from different threads at the same time. This is not good for performance. And so one of the most common things to do is actually to use different command tools for each different frame, each different thread, and for each different frame. Because again, another flag here was reset command buffer. So we take command pool reset command buffer. That lets us reset individual command buffer, right? Empty the memory of individual command buffers. That can be used, but the problem with doing that is it doesn't exactly it's not optimal, let's say, right? Because you're doing allocations, deallocating some parts of it. So if let's say two command buffers are being allocated, one after the other in alternation, right? Different commands have different size. And then just one of the command buffer goes away and you try to allocate other commands on it. If the commands don't fit in the same places, you start wasting space. It's the fragmentation problem. So yeah, you instead reset the entire command pool, right? You just say every single command buffer that was allocated gets automatically reset all at the same time. Then you don't have a problem. Just start again. So each frame should have its own command pool. How many frames do we have? We want to use 3 frames. Okay. That is a constant. So I'm going to write it up here. It's a constant for now, but you can change it. We can change it later. It's max frames in flight. That is as many frames as I can have concurrently at the same time. But it could just be called frame flights as well, because they're not maximum. They're really just, let's name it to none frames. It's simpler. Swapchain image count. The 3 here, the magic number, is also actually num frames. So I'm trying to match the Swapchain images with the number of frames I want actually to be existing. But if they're not, it will be an issue here, but it normally wouldn't be an issue. Anyway, so command pool. Okay. So since we want multiple command pools, so one reason that we still do it. Vector. We don't even need vector. This can be an array. Command pool and 3. So that's max. That's again num frames actually. So num frames number of command pools. This will remain the same for each of them, but for auto and annulled in command pool, so it should have an S on it. For each of these command pools, we will create a different, command pool. So now this creates one command pool for frame. Now that that's done, I will also allocate a single command buffer from each frame. You can normally use more than one. It's expected that you make more than one. But for the given task that we're trying to do, one command buffer is more than enough because we don't really have many commands. Unlike command pools, we're not creating command buffers. We are simply allocating it. So command, this is why buffer allocate info. This manually, if I had a mistake there, I'd put just the pool type, that will cause bugs in Vulkan, right? That's why the C++ version actually has this hard-coded and you don't have to bother with it. But anyway, here the command pool used to be manually added, which means I cannot just do the same command allocate info for all of them. Level, we create command buffer level primary. Primary command buffers are things you directly write in and directly execute. Secondary command buffers are things you write in, but you can't execute them. You instead add them to other primary buffers. So when I said you will use different command buffers on different threads, it means you cannot execute all of them that easily, right? And they cannot contain similar data. What you end up doing is instead of having all of them put together and then, sent to the GPU, you copy all of the different threads command buffers into the main primary buffer. It's not really copying, it's more like just linking them together. But yeah, command buffer count. Now, since we're using a single pool per frame, we just need one command buffer per frame, right? This for each command pool will go up there because command buffers will be allocated from there. We can allocate command buffers, the pointer to the function. Thank you. This becomes command pool allocate info, sorry, command buffer allocate info. This one should not be that. This is command buffers. Right. What is I? So you write 32 D. Index equals 0. Index plus plus. That's not the most clean thing to do, but plus index. That's more understandable. Here we do command pool. There's just one more thing required, right? It needs the size, the number of command. No, the command of allocate info has that. What does it mean? 3 parameters, but it's called with 4. So yeah, no electricity buybacks. We can verify this device, allocated info, and command infos. No allocation callbacks because this is just allocated from the pool, which means no new memory will be allocated here. Anyway, we got our command buffers. All good. Now we need to, actually render things. So poll event, this is going to check all the events that's input handling. It just checks if we want to quit or not. I'll leave it in the top, but that's not the best way of doing things. Anyway, after this, we have to get an image to render on. So we to acquire next image, device, Swapchain, timeout. So timeout is the max value for the timeout, which is std limit numerical limits u32 t max, which is u30 max basically. VK semaphore fence. So what are semaphore and fence? Semaphore is a GPU to GPU synchronization method, and a fence is a GPU to CPU synchronization method. We have to use at least one of the two. We will use a fence. And image index is current and current image index. This can time out, so that is one of its errors. So we can check, and there's that. There, the fence hasn't been created, so it's something we actually need to create. Again, each frame will have its own fence. So this is how it works in Vulkan. First, you can keep asking for images to acquire next image. Hold on, no way. We don't use a fence. We use a fence here, we use a semaphore here. what's the semaphore that we will use? Mm, let's check. Requirements to which job. Fence is a semaphore. Semaphore is a semaphore to signal. Fence is a fence to signal. So that is a design question here. So every time we render, then the semaphore that says render has finished, we use that semaphore to present. When we present, we will with the data, present comes back, and we want to acquire. Image acquired is a semaphore. So that should be image acquired semaphore here. Anyway, we'll first create them. We need one per frame anyway. std array pk semaphore frames. This one is image acquired semaphore. Second one is rendered finish semaphore. The last one is frame in use fence pk fence. All right. So each frame has associated with it if fence and two semaphores. Okay. The fence is something that we will use when we submit commands to the GPU, and we'll give it a fence, and we'll say, okay, once you're done using all the resources that you're using, once you're done rendering, signal this fence. And only after that fence is signaled do we start using like the render in the next frame. Because when we're using some resources, we send it to the GPU. Now the GPU is using it. And if we try to modify, things will go back. Like there'll be errors. What we want to do is we want to wait for GPU to be done with it before we start again. And so we use frames for that particular thing. Sorry, fences for that particular thing. Since we have created these, we should also make the synchronization. bk semaphore create info const semaphore create info equals the semaphore create info. The next is null pointer. bk semaphore create flag, so it's 7. There is more real flag on this denominator. Yeah, no flags. This is it. This is the semaphore create info basic. It's const expression. Like, it literally is a compile time thing, right? bk create semaphore device semaphore create info null pointer semaphore. This has to be bk check. You can check it. And we can just do a for each on this. So for auto and semaphore. Image acquired semaphore. There's this is image acquired become render promotions the same exact thing. Then use semaphore, so this will the fence now. Finish fence. Create fence. Fence. Yeah, on the fourth. So here we actually have a different fence to be used because, different flag to be used because we want it to be signaled. A fence can be unsignaled or signaled, right? Unsignaled doesn't reset. But when a fence is reset, what we mean in our particular mental model is that resources are still in use. And signaled means resources have finished being used because a GPU will signal it. However, when we start the first frame, no resources are being used because GPU hasn't even received anything yet. And the GPU will never signal us because, again, we never told it to signal us. Which means we will wait for GPU to signal, and the GPU will not have signal. And so we will wait for effectively nothing, right? Because we are waiting for the fence at the top. We can always wait for the fence at the bottom. Completely viable thing to do, really. But yeah, it is a personal narrative. However, you would like to do, right? Actually, I will use that. I will use that. I won't signal it ahead of time. So anyway, is running true? Yeah, fine. Actually, it does have to be signaled because we have to wait for it to have finished the thing. Okay. Now, running pump events, we ignore all of this. We don't really care. We want to keep an index of the frame that we are on. So, frame index equals 0. And at the end of every frame, we will increment the frame index. But frame index can also never go above particular values. Actually, frame index plus 1, all of this getting modulo by num frames, right? That's it. So that's the frame index continuously repeating. Current image index hasn't been created, so we will create it. And as you can see, like it's a local variable. We don't have fence. vk fence equals frame in use fences current frame index. So this is frame index. You can see this is actually unresolved. I mean, fence semaphores and nodes. That can be a bit irritating for plurals and singulars. What's your problem now? It became global somehow. Yeah, because we messed up the bracket there. Right here. Okay. That seems like it has corrected itself. Okay, here's what's going to happen. Step 1, we get to fence. This is wrong. We're not going to use the fence there. We will use the image acquired semaphore. Again, vk semaphore image acquired equals image acquired semaphores frame index. These are all, as you can see, these are kind of pointers to things, so we can pass them by values, and it's not at all a problem. So image acquired semaphore, that's passed there. So once image has been acquired, this semaphore will be signaled. All right. We can wait for fences. Device fence count as 1. The fence we use is the fence. Wait all equals it's all the same, but vk timeout is max value. So SCD numeric limits and 32D max. And that's it. There is a vk result because this can time out as well. Acquire next image actually has a non-failing result. So it may return what is known as vk THR suboptimal.
What does that mean? It means the swap chain is of a size that is not optimal for rendering. Similarly, there is also out of date, which says that the size is not the same as the size of the surface. It's out of date and it'll create the swap chain again. For now, we will just throw an error if we try to resize something or minimize. Okay. So wait for fences. So first we wait for the resources to be freed. So at this point, all resources of current frame, full index are free. Okay. I'm used to using LaTeX and stuff like that. Show the documentation. So this is a frame index are free. We then go for semaphore. We get the semaphore here, current image index as well, which will move down there. We have our image. Now we need to start the command buffer. Command buffers. We take command buffer cmd equals command buffers frame index. Okay. CMD. So again, vk command begin. Okay. Begin command buffer cmd begin info is begin info. vk command buffer begin as begin info. vk command buffer normally this shouldn't have anything because we are not using secondary buffers. None of this should truly matter. Secondary buffers need the inheritance info because they need to be able to get integrated into the primary buffers that we're using. But in this particular situation, we don't really care because, it's a primary itself. If there is a begin, there is an end. That's it. I will use braces to indent the commands. That way I remember the pairing. But this is like just personal taste, right? So vk render pass. Okay, so old Vulkan required you to create what is known as a frame buffer and a render pass and all of that, right? I'm not going to use it. I don't want to. So what I'm going to do instead, because that's kind of old school stuff. That's Vulkan 1.0 stuff. We are in the modern era. We don't need this. What I'm going to do instead is I will go to the device create info right here. And we have the features right there. Vulkan 1.2. So VK physical device features. Vulkan 1.2 features. Yeah, physical device, Vulkan 1.2 features, right? So physical device, Vulkan, features 12, 1.2. So features 1.2, there's an initialization. This can be a bit of a mess, but yeah. Structure, physical, device, Vulkan. I'm not used to typing on the keyboard I'm using today. So little annoying. We'll sing null beta, but probably we'll add more of these, right? I don't care, 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 I don't care.
Where is it? Where did the dynamic rendering? Did I? It's not here. Is it feature 112 then? Or is it 13? It's not in 11, so it's in 13. Yeah, dynamic rendering is true. So this is a core feature now, dynamic rendering. So I can just ask for this feature. And if I ask for it, the way to ask for it is to actually give it here in this chain. So this is why the pnext exists in create infos. I want to do something which is not a part of this physical device features, right? I want this features. So how do I give it to Vulkan? How do I tell it, hey, can you give me this feature? The way to do it is to say that I have these Vulkan device 1.3 features and pass this to pnext. Pnext is a void pointer. So it's not actually able to handle, these particular features directly. It doesn't know what type it is. And that's why we have these structure types. So this void pointer can be cast into this type again because it knows which enum it is. Anyway, now we have this nice little thing. This pnext itself can be a chain. So if I wanted Vulkan 1.2 features, I will do 1.2 features, put the features in, and the pnext of the 1.2 will be the 1.3, or vice versa. The pnext of the 1.3 can be 1.2. I don't know if there is a particular order for pnext for features. Sometimes there can be, but this case I don't know. Anyway, now that I have enabled dynamic rendering, what I can do is I can say begin rendering. So command begin rendering, right? It's a complete command in of itself. I need to give it rendering info. So rendering info. And that's all it needs. Rendering info means I can do UK rendering info. So you can see that it actually has a KHR version. That is from when it was an extension. But since now it is core, which means it is built into the language, I don't have to particularly pay attention. Should type rendering info is the create info. Pnext is null. Flags are 0. Rendering area is VK rect 2D. It is a rendering area. Rect 2D. Pressing the initialization, the offset, which is 0, and the extent, which is width, height. As you can understand, this is horrible. It is hard coding. It should not be hard coded. It should be based on the given Swapchain images, size, and stuff. So we have it somewhere. We have the Swapchain extent here, which comes from here, which we can move up here. So now we have Swapchain extent there. And so this extent is actually Swapchain extent now. Right. Layer count is 1 because we only created one layer count. View mask is view mask. Rendering view mask. What is supposed to be the value for it? Rendering info, view mask. Mask indicating attachment layers that will be rendered when it is not 0. Okay. But in this case, we just leave it to 0 because we just render on all the attachments. In this case, we only have one. Depth attachments, we don't use any. Stencil attachment, we don't use any. Color attachments, we use one. Okay. Which one color attachment? It is the current Swapchain image. How do we get Swapchain image? Well, we use this index that we get from current image index, and we get the image from Swapchain. How do you do that? Well, another thing I skipped already is here. So std vector vk image. Again, this can be an array. Yeah, this one has to be a vector. Swap chain images. Once we create swap chain, we take that swap chain images chart, device, swap chain image count. That count is chain image count, null pointer. Again, we cannot just use the image count that we had here, right? We had this. We used it in the create info, min image count. We cannot use, like, we will be asking for it, right? We will be asking for the value here. So we say swap image view count equals 0. So we're just going to do image view count equals 0 here. We will go in. We will check how many images we have. And then we will take Swapchain images. We will resize it. Not resolve, resize it to the size given by image count. And here we will switch an image count the data. Right? Now we'll write all the images into this Swapchain image, which is great. Another thing that Vulkan doesn't do for us in this, but this Vulkan did for us. It created images for us, right? We got them. We're done with them. The thing that Vulkan hasn't done for us is it hasn't created image views. What are image views, you might ask? Each image is just a resource. It's just data. Vulkan does not know how to read this data or what part of data we care about, right? So we can take one image, which is just memory, lot of memory, and then we can take parts of it, which are each independent views into this image. Each image view can be used as its own thing. And so in this case, we have an image, we have the memory given to us. So Vulkan has given us what memory we are to use. What it hasn't given us is how to access this memory, or in what way are we going to access this memory. So Swapchain views. And this image view is something we have to manually create. So for each of these swap chains, we will create an image view. So create image view, takes a device, takes a create info, so and image view, create info, callbacks with the null, TTR, and it will take it'll take a view, right? This is for view int 32. The index equals 0. Swap chain. So I don't need the index here. So swap chain. I can just say vk image. So image. I'll just do image here. Swap chain images. So for each image in swap chain image, we will create a view, which is image view. So that will be created here. This needs a vk check. And once the view is created, we'll push it into swap chain views on pushback. So be it. Okay. Now the view create info, which is uncreated here. We'll put that here. Image view create info. Post view create info equals traces plus dot yeah. VK structure direct image view create info. Don't come on. The next is null. Flags are 0. Image is the image. View types is VTA image, view type 2D because this will be a 2D screen. This is Swapchain format. What? Surface format, sorry. Surface format. Oh. Okay, it was just called format. It's just format.format. Components is VTA image, view component. And identities, which is nothing but just swizzling everything back into itself. Otherwise, you can, swap them around, R as B, B as R, and stuff like this. Sub-resource range. This is its own object, right? So dot decimal initialization. Aspect mask is VTA aspect color, so which is going to look at colors. There are no map mapping. There are no arrays. That's the default view create. What's happening here? Component. Oh. Component. Yeah, component mapping is a struct. So it takes RGB, right? So identity for R, identity for B, G, B, and A. So that tells it that, don't change anything, use all the data exactly as it exists. Anyway, components are done. This will create image views and will push back into Swapchain image views, which are unsized. The other thing we need to do is, since we created this, these image views need to go, and they need to go before the Swapchain image. Swapchain images are created by the Swapchain, and when you destroy Swapchain, it will destroy it. But destroy image views is something we need to do manually for each of the image views, right? So that, again, for auto, it's really views, Swapchain views, and each of those views gets deleted by themselves. So that clears everything. Color attachment, we take Swapchain view for the current image index. This is not for the frame. This is for a given image index. Okay. And since this is ampersand, we need to take a reference of this. What's your problem now? Oh, it means rendering attachment info. Okay, rendering attachment info. Honest attachment info. There should be an array if there were many of them, but since we only have one, okay, well, structure, rendering attachment info. The next is null pointer. Image view is, so here's where the image view comes in. Image view is the current Swapchain image view. Okay. Image layout is VK image layout undefined. So image layout is how the image is placed in memory, right? They can be moved around because different things are differently optimized. So when you're reading from it, might be differently optimized compared to like when you're reading on a shader, it is differently optimized compared to when you're transferring data to it from the CPU, because CPU will keep it row by row for a whole image, while shaders prefer tile by tile, right? They prefer like groups because they can do derivatives on it and stuff like this. So based on that, we do undefined right now because we don't care what the layout is. We're going to clear it. Resolve mode, we can resolve mode none. is always something that we've used for multi-sampling and all of that. But since we don't resolve at all, we don't particularly care. Load opt. So we say load op clear. So load op is basically just load op is basically how do you load each of the pixels. So you could do load op load, which loads the old image. You could do load up clear, which will clear the whole screen. Load up don't care. In case you will render on the home screen, you don't care what the data existed. So you don't even want to clear it. That's too much work. So, you might use that. But right now we are using clear. So we will do color, clear value because this is a color. There's no float 32 is an array of 4. Maybe just swap that with that. And we need 4 floats. What I will do is I'll look for a color. Cauliflower blue RGB. Blue. 100, 149. That looks wrong to me. Microsoft cauliflower blue. Or Excel cauliflower blue. Yeah. Is Excel cauliflower blue property. Yeah, ARGB value 6495 ED. That's hex. 6495 ED. Hex to RGB. $64.95 ED. That gives us 100, 149 to 54. So 100, 100.0 by 255.0, comma 100, 149, 237. 149, 237. Right? That is a clear value. Color and another one to close that. Okay, resolve image layout is retray image layout under cloud. Okay, attachment info is done. We just have one attachment info, so we give it to this. It's still easier than doing the render pass. Render pass can be a lot more annoying than this. Begin render pass. This will be end render pass. So end rendering is CMD end rendering. And if we don't actually do anything inside, we just clear it and we call it a day here. So we just ask if we're gonna render something and we leave it there. So with end command buffer, the command buffer is complete and we need to submit it. So we say submit in. So we say submit info is something we need to create anyway. So might as well create it first. Designate initialization, VK structure type, submit info, next is null pointer, wait semaphore count is 1. So what's a wait semaphore? Wait semaphore is what we will wait for before this particular task executes, right? And in this case, we need to wait for this image acquired semaphore to have become available, right? Like for this image to have been acquired. So we will provide the image acquired semaphore. Wait destination stage mask. So This is a stage mask. So VK stage mask. Well, pipeline stage mask. Yeah. VK pipeline stage flags stage mask equals this is flag bits, which is VK pipeline stage color attachment output bit. So color attachment output bit is where the color, is written to the screen. You should actually do it at the top of the pipe. Doesn't really matter actually in this particular case. I believe it can actually be null. We can check submit info. The destination stage is an array of pipeline stages at which each corresponding semaphore weight will occur. So that one semaphore that we have, it will occur at color attachment. Yeah, color attachment output bit is correct. Because loading happens right there, right? So we will wait for it to finish loading, finish doing this, then it will do a load. Last chat will delete it. Yeah. Command buffer count. One command buffer. It's the CMD buffer like we just used. Signal semaphore is rendering finished semaphore info. So just like the image acquired semaphore, we need to get the other semaphore. Semaphores, and we take it in the current field, so frame index. Okay, then we provide this. So once the frame is available, like once it's finished doing this whole task, it will write to rendering finished semaphore. Submit info, and once the submit info is ready, we will do VK queue submit. It requires the queue, which is the direct queue that we got at the start. Submit count, we just have one submit info, the submit info there. And here is the fence. So that is the frame in use fence, right? So in this case, I think we just got it out as a fence, right? We could check it. I think this can return. Yeah, it does return a VK result. So both become and end, I think, can return. Meanwhile, all the commands between on the command buffer cannot return errors because there's nothing really to fail. They're just writing data into the command buffers. All right. Command buffer submit. This is done. Once it has submitted, we have to present. So we keep result. So it's VK swap chain. Present. VK image present. VK result. Okay, Q present of it. Q also chart takes the direct queue, which does have present on it. It takes present info, right? And this too is a VK check. So VK check. We need to create the present info here. So VK, there's a info chart, or there's a info doesn't initialization, base structure, type doesn't info chart. The next is null pointer, wait semaphore count. So here again, one And the wait semaphore is the rendering finish semaphore. So what we're going to do is when the rendering finishes, we're ready to present. So whatever this signals, this will read from swap chain count one, the swap chains. So you can actually present on multiple swap chains. You can present to multiple windows, right? So if you actually use multiple screens and you play a game that extends across these screens, these days you have ultra wide, but back in the day you would want that. This would allow you to actually use multiple swap chains together. We only have the one swap chain, so we don't particularly care. Image indexes. Again, there's only one image index we have, so current image index, right? The results. Really? What? What are the P results? Hey, we can check. This one is submit info. Get result info chart. Right? P results is a pointer to results, elements of soft chain count entries. Yeah, so I can use that. It just being up when I need the list of things there. Oh, that just the one. Then the finish summer. Alright. And that's present info. This presents it. Once it's presented, we're kind of done. So we finish here. If I am correct, this is going to work. And it is not. Fatal error. Lovely, isn't it? If semaphore is null, it must not have any uncompleted signal or wait operations. It's 2%. Ah, yes, I did forget certain things. Since we use rendering, the new rendering API thing, it doesn't synchronize everything automatically anymore. Earlier, there was a thing like when you started a render pass, all your data will get synchronized, which doesn't exist in rendering because it allows you a bit more flexibility, which means the driver doesn't know what you want. So you want to do what is known as a pipeline barrier. So VK image barrier, image memory barrier to image memory barrier to that pen doesn't matter. So I call this acquire to render barrier, and this is gonna be long. So structure type VK structure type image memory. This is one of those things people like abstract away as soon as possible. So stage mask. So VKs. Those VK pipeline stage of the pipe bit that says at the very start of rendering system. Okay, that's where we start looking from. Source access mask is none. Destination is VK color attachment read bit KHR. So not read bit actually, we care about write. So when the color attachment is being written to, which is the loading, right? This not loading, but the clear happens at the rendering pass there. Destination stage, we can access to right color attachment right bit. Oh, I made a mistake here. Pipeline stage 2, not top of the pipe, but color attachment output bit. Yeah, hold it. VK image undefined. Right? New layout is VK image layout optimal. Color attachment optimal, right? Okay, we can actually check this. Rendering attachment info. Image layout is the layout image will be during the rendering. So that should be color attachment optimal. Source Q family index. VK Q family ignored. We don't care about this because we're going to use the same Q family throughout the process. This image, it asks me for the current Swapchain image, is the image, not the view. So Swapchain images, current image. Sub-resource range, it's the same kind of stuff we've already done before. So VK aspect color bit, base map level is 0, level count is 1, base array level is 0, layer count is 1. Okay. And that gives us sub-resource range. This is the first barrier we will use. I will copy and paste it because there is another one which is render to present barrier. So this will prime everything for being presented. Instead of top of the pipe, this is color attachment output bit. So it's this one moved up there. It's this one moved up here. This stays bottom of the pipe. So bottom of the pipe says act once everything else is done, right? The source becomes old layout and this one is present at image. Image, layout, present, source, PHR, right? So that is ready to be presented. The rest remains the same. Now we have a dependency info acquire render dependency equals this. It's a synchronization 2. We don't necessarily need to use this. We could have used synchronization 1. But I like using synchronization 2. The next is null pointer. Dependency flags is 0. Memory barrier cost is 0. Buffer is 0. There's one image layer barrier, like image barrier count. This is the acquired to render barrier. Okay. And similarly, we have this, which is the render to present. And just like barrier, this will be called dependency, right? And we'll copy the barrier and that will be right here. So now we have these dependencies in the command buffer, right? After we begin, but before we actually, oh, hold on, this is in the wrong place. Attachment info. Yeah, that is most definitely in the wrong place. This actually can be made outside here. This is why I like using these particular functions, okay? The issue with this is the Swapchain images, we don't have the current image index, right? I can make these one per frame. That is entirely possible. But instead, the sort of nicer way of doing it is to not write the images, provide it here, go to the rendering begin. Before that, I will do VK command pipeline barrier. I provide the command buffer, I provide the acquire to render dependency. Similarly, I do it after the ending, which is render to present dependency. Those should handle things for me. Finally, every start of the frame, when I get the current image index, when I do this, I should also take the acquire render barrier dot image equals Swapchain images current image index, right? And I'll paste it there. Same-ish thing, but this one will be rendered to present barrier. And the rest is the same, exactly the same. This is perfectly fine, right? and it's going to give us an error because there is a feature I need for synchronization, which we haven't enabled. Features there. It's called synchronization. No, synchronization 2. So large should work. Oop, was wrong. In declaration, of course. This is not C. It's C++. Compiler can't reorder things for us like that. Read after write hazard. Fence is not we cannot handle. It must be unsigned. Fence must be reset before submitting. Of course. So here's what has happened. So we waited for fences. We acquired the image. Okay. And after this, like the fence has to be reset. One of the things I normally do is after I acquire the image, if it is suboptimal, I recreate the entire thing, right? And this fence, if I signal it, if I reset it, then it won't work and we lose this whole thing. So instead, when I reset it, when I redo the swap chain, I don't reset it until all of it has successfully completed. So normally I reset it here. Okay. Reset fences, device, one fence, and that's the fence, right? So that should be fine now. Teller attachment. Oh, I think I know exactly the issue. F. Well, let's do this first. F. Okay. The synchronization trouble that we're talking about. So right after read, the problem is here, when I do the dependency, I say top of the pipe. Look, it's here. I say top of the pipe, but in reality, I'm actually depending on the color attachment output of the previous frame. Right? So when the previous frame wrote the image, I'm actually dependent on that. There we go. No synchronization issues. See? That's config blue. We have cleared the screen. That's the end of today. Next time, I will be making a trial in database. All right. Then I guess. And calves. And my non-binary pals. All right. Cheers.